Hello everyone, I'm Brian Macon, and we are now going to begin learning about analytic trigonometry. And before we can look at some really cool applications, we need to build some foundation, and in this video we're going to define the inverse sine function. So let's get started. Before we define the inverse sine function, let's review some information about inverse functions in general. Two functions f of x and g of x are inverses if and only if f composed with g equals x and g composed with f equals x. To illustrate this, let's use a specific example. We know that the cube function and the cube root function are inverses of each other. For example, if I take the number 2 and cube it, I get the number 8. Then, if I take the cube root of 8, I come back to the original number of 2. So in other words, the cube and the cube root are undoing each other. They're inverses. So let's work through this symbolically and compute the composition for f of x equals x cubed and g of x equals cube root of x. So let's begin with f composed with g at x, or f of g of x. And this equals f of cube root of x. And since the function f cubes its input, we have cube root of x quantity cubed. Rewriting the cube root as x to the power of 1/3, then multiplying the exponents of 1/3 and 3, we get x to the power of 1. So in other words, f composed with g of x equals x for our two functions, f of x equals x cubed and g of x equals cube root of x. Now let's evaluate the composition in the other direction. That is, let's find g composed with f of x. So this equals g of x cubed, which equals cube root of the quantity x cubed. Rewriting the cube root, the 1/3 power, then multiplying the exponents of 3 and 1/3, we get x to the first power. So again, g composed with f equals x. And this shows that the two functions are inverses of each other. Now once we know that two functions are inverses of each other, then we can use inverse notation. So to write the inverse of f, we use a superscript of -1 on the name of the function. Now it looks like f to the power of -1, but we want to be careful because the -1 superscript does not indicate a reciprocal of 1 over f. Additionally, we don't read or say this as f to the -1 power. We say it as f inverse of x. So for this example, we can say for f of x equals x cubed, then f inverse of x equals cube root of x. And similarly, we can say for g of x equals cube root of x, that g inverse of x equals x cubed. So in general, for a function f and its inverse, we can write f composed with f inverse of x equals x, and f inverse composed with f of x equals x. As we just reviewed, inverse functions undo each other, which we write mathematically as the compositions we just stated. There's some additional relationships between inverse functions that can be noted. The first one is that the graphs of inverse functions are symmetric to each other about the line y equals x. So here we have graphed our examples of y equals x cubed in blue and y equals cube root of x in red, as well as the dotted line y equals x in black. And this is in a viewing window of -6 to 6 on the x-axis and -4 to 4 on the y-axis. Let's note that the two functions are mirror images of each other over the line y equals x. And symmetry over the line y equals x is true for any two functions that are inverses of each other. Another relationship is that the domain of f is equal to the range of its inverse, and the range of f is equal to the domain of its inverse. Another way to state the relationship between domain and range is by writing that if f at a equals b, then f inverse at b equals a. Now, there's one last very important note to make in our review of inverse functions. And in order for the inverse function to exist, the function f must be 1-to-1. So in other words, for each value of y in the range of f, there must exist one and only one corresponding value of x in the domain. Now, visually, this means the graph of f will pass the horizontal line test. If f is 1-to-1, then we are guaranteed that the inverse is a function and will pass the vertical line test. In some cases, we may need to restrict the domain of the function in order to make sure it's one-to-one. An example of this is f of x equals x squared. Considering the graph of the parabola y equals x squared in the window negative 10 to 10 on the x-axis and negative 10 to 10 on the y, we note that it fails the horizontal line test. For example, the value of y equals 4 corresponds to two different x values of negative 2 and positive 2. I've drawn a few dotted horizontal lines to illustrate that the square function fails the horizontal line test. Now, to guarantee that the square root function has an inverse, we can restrict the domain of f of x equals x squared to be x greater than or equal to 0. That we can see graphed here in the same viewing window. I've also plotted the point 2, 4 in particular. And this new function with restricted domain is one-to-one. It passes the horizontal line test, and thus its inverse, which is the square root function, will pass the vertical line test. Here we've graphed y equals square root x in the same window, and I've plotted the point 4, 2 that's on the graph of the square root function. And again, since the square with restricted domain x greater than or equal to 0 is one-to-one, then its inverse y equals square root of x will pass the vertical line test and is a function. Now we don't need to restrict the domain of every function to guarantee its inverse exists. We didn't need to do that for the cube function, but there are some functions where we do need to restrict the domain to make it one-to-one, as we have seen here with y equals x squared. All right, finally, since we're done with our review, let's use this knowledge about the relationships between a function and its inverse to develop the inverse trigonometric functions. So let's begin by defining the inverse sine function. If we graph y equals sine x, which has a domain of all reals and a range of negative 1 to 1 inclusive of the endpoints, then we can note that the function fails the horizontal line test and therefore is not one-to-one. So to define the inverse sine function, we need to restrict the domain of the sine function to be negative pi over 2 to pi over 2 inclusive. This segment of the sine function will be one-to-one. Now, there are other restrictions that we could use for the domain to make the sine function one-to-one, but the one that's used here is a universally accepted restriction. Now that we have a restricted version of the function y equals sine x that's one-to-one, whose domain is negative pi over 2 to pi over 2 inclusive, and the range is negative 1 to 1 inclusive, we can define the inverse sine function to be y equals inverse sine of x if and only if x equals sine of y. Remember, we interchange domain and range, and thus the domain of the inverse sine function is negative 1 to 1 inclusive, and the range is negative pi over 2 to pi over 2 inclusive. And we can take the restricted version of the graph of y equals sine x and reflect it over the line y equals x to obtain the graph of the inverse sine function. On the image here, in red, we have graphed y equals sine x over the domain, negative pi over 2 to pi over 2 inclusive. We have also, on the same coordinate grid in blue, the graph of y equals inverse sine of x over the domain, negative 1 to 1 inclusive. A few notes to make here. There are two ways that we can denote the inverse sine function. One way is to write the name of the function as arcsine of x, which we spell A-R-C-S-I-N. A second way to write the name of the function is to use the superscript of negative 1 on the name of the sine function. So in other words, we write the letters S-I-N, then have a superscript of negative 1. And when using the superscript of negative 1, we want to be careful not to interpret this as an exponent. So in other words, inverse sine of x does not equal 1 over sine of x. And lastly, most calculators have the capability of calculating values for the inverse trigonometric functions. And in most cases, the inverse trigonometric functions are on the same key located above the respective trigonometric function.